Good afternoon, and welcome to today's webinar, Understanding and Solving Extrusion and Coextrusion Problems with Simulation. My name is Jim Colari. I'm the Editorial Director of Plastics Technology, and I will be your moderator for this session. Our presenter is John Perticoulias. Dr. Perticoulias is a licensed professional engineer with more than 30 years in the plastics industry. He holds both a Bachelor and a Master of Engineering degree from McMaster University and a PhD from the University of Waterloo in Canada. John is co-founder of Compuplast, providing simulation software and services to the polymer processing industry worldwide. Please feel free to ask questions at any time during John's presentation. Simply detach the questions pane from the panel on the right-hand side of your screen and type in your questions. We will get to as many as possible following John's presentation. It's now my pleasure to turn the presentation over to Dr. John Perticoulias.
Thank you very much, Jim, and welcome everybody. So today I'd like to give people an overview of how simulation is applied towards solving, or first of all, understanding the reason for some extrusion and co-extrusion problems, and then providing a more direct solution. So simulation provides us with a better understanding of the process and the complex relationship between the variables. Simulation is much more efficient than experimentation, and simulation avoids costly physical trial and error development that some people often use. With the simulation, we can also improve our accuracy with calibration from experimental data. Quite often, some of the parameters in the simulation have to be estimated, and once we get a little feedback from experimental data, we can calibrate those parameters that are estimated to give us better results. And we do need some experience or training for proper interpretation of the results. That is, the color contours and the graphs that the simulation give us need to be interpreted in order to understand what they mean. And then once the process or the problem is better understood, simulation can help optimize the process or provide a more direct solution to the problem. Some of the problems that have been solved with extrusion simulation are shown here, and they vary from degradation to unmelts to interfacial instabilities, dyed drool, lines or wrinkles in your product, or film web breaks. Today, the topics that I'm going to present include excessive screw wear, melt temperature variation and excessive melt temperature, polymer degradation in general, unstable profile extrusion, and co-extrusion instability. The simulations are performed with the Compuplast Virtual Extrusion Laboratory suite of CAE tools. So let's get started with the first topic, which is excessive screw wear or damage. The first image here shows discoloration, which is due to high surface stress. We initially thought this was due to excessive temperature, but we can see here the rather abrupt change between the chrome color, shiny chrome color, to the dark blue color. And this is at the end of a groove feed section where a high pressure force is created. And if this was temperature, because metal is a very good conductor of heat, we wouldn't expect to see such an abrupt transition in the color. So this is due to very high surface stress in that region due to the high pressure. The next image shows the flight wear due to very high surface stress. You can see here where there's a definite flight width, and then narrowing of the flight right down to a knife edge at this point. And the pellets have actually worn away the metal of the flight. And here is an image of another screw that's had excessive force or shear stress put on the surface to the point first where the screw discolored, and then where that chrome layer was actually scraped off. you can see in certain patchy areas where we had the pellets scrape off the chrome. And in the extreme case, we can have this catastrophic failure of this 6-inch screw, which has failed, and it's not in the feed throat due to a cold start. This has failed in one of the thickest parts of the screw. And so we're going to analyze why this, how this could have happened. So one of the parameters that we use to understand how an extruder is performing is the so-called solid bed ratio. And when you have an extruder here in this representation, we have the pellets coming in, and early on the pellets form a solid bed. And as the solid bed moves along, we start to get a melt pool being created between the pushing flight and the solid bed. And as we move along, the solid bed should get narrower while the melt pool gets wider until ultimately all the solid material is melted. And then we might have a mixer add some additional pumping after the mixer. Now, based on some visualization experiments through a glass window extruder, we can see here the channel and the solid bed and the melt pool. When the polymer melts, it becomes amorphous, and you can see right through, it's clear, you can see right through the material to the screw root. So this is the melted material, and this is the solid bed. And the solid bed ratio is simply the solid bed width divided by the channel width. And as you might expect, this solid bed width is the same as the channel width early on in the screw, early in the feed section, and then gradually reduces down to 0. So it should have a value between 1 and 0. So we're looking at the ratio of solid bed width to channel width, and it is an indication of the material melting rate. Now, if we consider this screw, which has broken, and we look at the solid bed profile, we see the solid bed starts off at a value of 1. The channel is all solid material, and then it starts to gradually reduce along the screw length to some point where here it starts to then increase again. And this doesn't mean the material is re-solidifying. It means that there's a change in volume of the solids channel. This is a barrier screw, so we're introducing a barrier flight, and the solid channel, or the channel area where the solid material is getting smaller. And so the ratio of the solid material to the solid channel width is changing. And so it helps to look also at the amount of unmelted material. So the black line is the solid bed ratio, or width, corresponding to the axis on the left. And the blue line is the amount of remaining unmelted material corresponding to the axis on the right. And it's the relative amount, so they both start at 1 and go to 0. And so we can see here that when the barrier section is introduced, the solid bed ratio starts to increase, but the material is still melting. The melting rate is still fairly constant. What's happening is that the reduction of the solids section of that screw, that volume is reducing faster than the rate at which the polymer can melt. And as a result, you're squeezing the solid bed and spreading it to make it wider and wider and wider until ultimately at this point it goes to a value of 1, which means that the channel is full of solid material. There's no more melt pool in there, and here is where you're restricting your melting rate in your barrier screw. Now you can see here that we are still continuing to melt, but at the end of the barrier screw we still have about 30% unmelted material. So the solids channel depth reduces at this point here and causes a wedge force of the solid material, which can deflect the screw. Now typically this results in normal flight wear and barrel wear, but in this case the channel depth reduction was too abrupt. You can see right in here that it was done in less than 1 turn, and we had 30% unmelted material, and this resulted in excessive unbalanced force on one side of the screw, which results in a periodic screw deflection. This leads to what's called cyclic fatigue failure, and if you consider the number of cycles when the screw is running at 75 RPM, over 60 minutes, 24 hours, and 365 days, we can have almost 40 million cycles per year. Unfortunately, these screws did not survive a full year. I think it was 11 months. And initially, it was thought that it was a mechanical failure due to some defect in the metal. But when the third identical screw breaks, then we start to look more seriously at the design as being a problem. Once we understand that we are not, the designer assumed that the polymer would be all molten by this point, the simulation shows us that there is solid material left, and we are trying to force that melting in a very short distance. This causes a deflection. We know that this is a poor design then. And so if we want to make sure that we do not get into a condition where we're trying to force material to melt in a short distance, we use less abrupt geometry changes in our screw, more gradual closing off of the barrier sections, and then we have a continual reduction of the solid bed width and a reduction of the solid material, the amount of unmelts, well before the end of the screw, and then the mixer to homogenize, and we have a much more stable operation with minimal wear on our system. So this is a good result, which we'd like to see in our design, versus the previous poor result in the design. The next topic is melt temperature variation, and it probably accounts for, I would say, close to 80% of our consulting work and the problems that people face in the industry. And to demonstrate this, I want to use two 1 melt index materials, a 1 melt index low density polyethylene and a 1 melt index linear low density polyethylene. And because they both have the same melt index, a lot of people mistakenly believe that they are very similar materials and process in a similar fashion. But if you look at the full viscosity curve shown here, the melt index range is at the very low shear rates. In fact, the shear rate at which the melt index is measured is 2.4 times the melt index. So the melt index here is measured at a shear rate of 2.4, but the processing range is an order of magnitude or two higher than the shear rate range. And at this point, we can see that there's almost a 3 times difference in viscosity between the low density and the linear low density. The linear low density is more viscous. So if we have a screw that's been designed for the low density, so here I show a kind of a general purpose compression screw, and I'm going to perform a simulation on this screw design. And here's the result. The black line is the solid bed width ratio, so you can see it's going down gradually and reduces to 0 before the end of the screw. So all the material has melted. And the blue line shows the temperature development corresponding to the right axis. At 75 RPM, this extruder is producing 157 kgs per hour, and the bulk average melt temperature at the end of the screw reaches 208 degrees Celsius. And this is acceptable performance. Now, if we look at the temperature across the gap at the end of the screw, this gives us an idea of how much temperature variation we might have through the melt at the exit of the screw. And we can see here the maximum temperature reaches 212 degrees, and we have an average of 208, and so it's relatively low temperature variation, so this is acceptable performance, and we wouldn't expect to see too many problems from this extruder with this material. Now, quite often extruders outlive their initial use, and people often change resins without really considering what the effect might be on the process. So now let's take the same screw and put in a 1 mi linear low density polyethylene, again running at 75 RPM. Now, because the linear low pumps a little better than the low density, we're getting a higher output, 173 kgs per hour. the solid bed ratio is still reducing and reaching 0 before the end of the screw, meaning that all the material has melted in the extruder. But if we look at the bulk average temperature, we see that the final bulk average temperature is over 30 degrees higher than with the low density, 239 degrees. Now, this is just the bulk average temperature. If we look at the temperature across the gap at the end of the screw, we see that the peak temperature is 253 degrees C. And when we tell our customers that we believe that their temperature is higher, they quite often say, but my thermocouple doesn't indicate this. And to demonstrate why this might happen, I have this graphic here where I have, this represents an adapter where the polymer is flowing, and we're holding the adapter at 200 degrees Celsius. And the customer may have a melt probe, which is in maybe about 1/8 of an inch into the adapter, and it's reading 215 degrees Celsius. And they would never see the high temperature that's flowing in the middle of the adapter at 253 degrees Celsius. Now, if you have such a temperature variation, and I've seen close to 100 degrees Celsius temperature variation in a melt stream, you cannot expect the die to smooth out this large of a variation. And so quite often when people call us about their dies not performing properly, we will ask a lot of questions about their extruder and how it's working, because very often it is the melt temperature variation coming off of the screw that's causing a lot of the downstream problems in the process. So moving on to the next topic, which is polymer degradation, again, probably dealing with melt temperature, but more importantly here, we're looking at residence time of the material inside the system. And one of the problems that we see is when people replace a breaker plate, which would be sitting at the tip of the screw here, with a slide plate or hydraulic screen changer, they often don't modify the screw tip. The hydraulic screen changer needs some distance before the breaker plate to establish some pressure force on a hydraulic seal, kind of a tapered silicone seal here that's in this area that prevents the breaker plate from leaking. And so they have 3, 4, 5 inches of length in this area, and if the screw tip stays where it was originally, there is a large volume that has a very low shear rate and very low shear stress. And let me explain why this is a problem. So whenever we have polymer flowing in a channel, we have some velocity profile. And if we plot the shear stress, which is, the shear stress is simply the viscosity times the shear rate. If we plot the shear stress in this same geometry, the shear stress is maximum at the wall, and it's minimum where the velocity is maximum. So here we have the maximum velocity, the shear stress is 0 in the middle, but we're more concerned about the shear stress in the wall. And 90% of the time when we say shear stress, we mean wall shear stress. Now the shear stress at the wall is what performs the scrubbing action that results in what some people refer to as a self-cleaning system. And so we want the shear stress at the wall high enough to maintain a clean surface. Otherwise, if the shear stress is too low, we get a layer of stagnant polymer sitting at the wall, essentially not moving, and the polymer will just use as much of the flow channel as it wants. So you'll hear terms like rat holing or tunneling through the adapter or through the flow channel. And so we want to make sure that our wall shear stress is sufficiently high to keep that wall scrubbed. And the question is, what is high enough? Well, we found, and I'll explain how we get these numbers, we found that polyolefins generally require, or we recommend, a design shear stress of about 30 kilopascals. This has some safety margin in it. And PVC, we recommend a little bit higher wall shear stress of about 35 kilopascals. And this will effectively ensure that the polymer is wiping itself against that wall and scrubbing that surface. So the first thing we do is we make sure we don't have large volume areas, and so if we are going to change the screen changer, we're going to modify the screw and extend the tip so that it is closer to the breaker plate. And the next thing we're going to do is put in a bushing that will reduce the diameter down to an acceptable diameter that has an adequate shear stress that avoids stagnation of the polymer along the wall. And you wouldn't believe how much discussion there is over the design of this area. And we came across this design or end result that was provided to us by one of our customers. This is the downstream section off a 6-inch, 150 millimeter screen changer. This is where the breaker plate would be. And the designer of this adapter felt that this hemispherical transition down to about 45 millimeters or 1 3/4 inch adapter, the designer felt that this hemispherical transition would be the best design for this system. However, you can see that the polymer didn't agree. We can see here the discoloration and the burning of the material. This is PVC, and PVC will show you where the shear stresses are very low because it'll start to degrade. And it's like a cancer. It'll just grow and grow and grow and ultimately get picked off and may appear in your product. So we analyzed this transition. They gave us the flow rates that they were running, and we estimated the material rheology that they had. And this is a 2D finite element simulation because the flow field is axisymmetric, so we don't have to go to full 3D. We can use the 2D simulation. This is the axis of symmetry. This is where the breaker plate, the outlet of the breaker plate is, and then you can see the transition down to the adapter size. And the colors you see on this image are the shear stress. And of course, the shear stress in the middle is 0, so it's blue, and red is the high shear stress. The highest shear stress is here where the diameter is lower. And we're more interested in the shear stress along the wall, which is shown on this graph. So here is the high stress in the adapter region, and then you can see the shear stress reduces down to this valley in this region right in here, and then comes up again just near the breaker plate because the flow off the breaker plate is essentially a plug flow, and then that plug flow with a constant velocity is changed to a parabolic flow as it moves down into the adapter. And so we end up with this low shear stress region right in here, and this is our line showing our 30-35 kilopascal design value recommendation. And we can see how the observed degradation in the system corresponds very nicely with the very low shear stress region on this adapter. Once we understand where the problem is coming from and why we have this problem, we can then start to evaluate designs that maintain a higher shear stress on this surface. And we'll find that ultimately the solution is quite opposite to what that design had. We have this more convex geometry change, and if we modify it, if we plot the shear stress along this surface, we see that the shear stress along the entire surface is above the critical value, and then we can avoid having the buildup of degraded material on that surface. And so we modify our design to have a more convex shape rather than the concave shape that they had initially designed. Now, how do we come up with this shear stress, this critical shear stress value? Well, by analyzing systems, especially something like a flat die. Here we see a siding, a flat die used to produce vinyl siding, and this die had the pitting that occurs when PVC degrades. It forms corrosive byproducts that can get under the chrome and erode away at the base metal of the die, requiring refurbishing. The above picture is the refurbished die. We were more interested the original after it had been in use for a while, how it had worn out. And what we do is we simulate the flow conditions in this geometry, and we look at the shear stress on the surface. And once we have the shear stress values along the surface, we go back to the geometry and we measure back from the edge. Let's call it 3 inches from the end is where the pitting starts to occur. So everything is good in this channel, all along here, and just about this area right here, we start to get the pitting. And then we go back to our simulation and we measure the same distance back from here, and we pick off a value of shear stress. And that's how we determine the absolute minimum shear stress that will maintain the surface clean and avoid stagnation and degradation. We put a little safety factor on that, and then we tell our equipment supplier that the next die you build for us, we want you to ensure that the shear stress on that surface is above this critical value, and that will greatly reduce the number of times you need to take that die down and send it out for refurbishing. The next example is degradation in a blown film application, and it deals with more first quality, and then I'll show you the degradation part. But basically, it deals with a spiral mandrel type distribution system. This is a representation, not the exact die that was used. And the problem was that they could see these lines on their bubble, very sharp. They weren't what's typically called referred to as haze lines. They were more well-defined than haze lines, and they were, of course, equal to the number of spirals in the system. And everybody assumed that the problem is the design of the spirals, but they don't know exactly where or why, what in the spirals is causing this problem. And this problem here is that they were producing greenhouse film, so you can see the lines in the film. I think this is a better view here. So you can see these lines in the polymer sheet. And the problem was that the sheet was degrading prematurely along these lines, indicating that they perhaps had a higher residence time than the rest of the sheet. So here is where we do a simulation of the geometry under the process conditions they were running and try to see where there might be a problem. This image shows a 3D finite element simulation of the spiral mandrel flow field, one section of it. It repeats. It's periodic around the circumference. And so we take one section, and we're showing here the pressure distribution through the system, and this looks fine. Here is the flow variation at the end of the spiral, and that looks very good. There is no indication to show a reason for a line. And one of the powerful tools of 3D simulation is that you can use path lines. They're almost like streamlines, but in 3D we call them path lines, which can trace the flow of the material. And here I'm showing 4 periodic sections where I have placed path lines at the start of the spirals. So I've placed a few path lines near the wall at the start of the spiral, and we can see that some of the path lines are going up and back into the channel from the previous section. So some path lines go forward, but then some path lines actually go back to the previous section. The path lines going this way merge with the lines going this way, and they form a stagnation region in here where the path lines are avoiding, and right above that stagnation region we have a weld line. And so the material flowing from this direction with the material flowing from this direction forms a weld line of the 2 flow fronts, and this weld line is formed with polymer in this very low stress region that has a very long residence time and more prone to degradation. And so whenever we have these weld lines formed with slow-moving, high residence time material, we can expect that area of that film will perform differently. A similar result has been seen on the so-called flat spiral dies or stack type dies. If we analyze the spiral distribution system in here, we've seen systems that have the same problem. Here we're showing a color contour of the shear stress on the surface along with the path lines. Blue is low stress, red is high stress. And we can see once again that the geometry was not done correctly and that the path lines go up and back into the previous channel while some lines go along that channel and up. And right where we have the low stress regions, and you can see they're periodic all the way around, we have two flow fronts meet and we end up with these weld lines. So once we understand this, the solution is to optimize the die geometry to eliminate the backflow and ensure that all path lines are moving in the same direction along the spiral channels. Then you know that you're not having a stagnant region and you're not forming any straight through weld lines that will give you this problem. So,
in order to avoid degradation, we need to ensure adequate shear stress in all flow channels, which means first proper channel design and then also proper operating conditions. Because if a channel is designed for 200 pounds an hour and you're running it at 100 pounds an hour, it's quite likely the shear stress will be too low and you may expect problems.
The next example is an inconsistent extruded profile shape. This is a windowsill profile, and the customer was complaining of unstable production. They couldn't run faster, and they couldn't maintain the tolerances. The tolerances would go out of spec. And so they wanted a method that would allow them to increase the production rate. The die was constructed as typically is by plates. So here is an exploded view of the die, kind of a front view and a top view to produce this part. And the simulation of the various cross sections in this die showed a very unstable flow die. We look here at the velocity distribution of how the polymer would like to flow, each one of these cross sections in the die, we see that there is a high flow, the high flow region kind of migrates from the side to the center, to the sides, back to the center, and the polymer follows this snaky pattern through the system. And so at a given rate for a given material lot, they managed to produce something, but then when they changed lots or tried to go faster, the polymer just didn't have enough time to move across the system and balance out, and so they went out of spec. The solution, so the problem here is we determine is cross flows, these material flowing across the die, which is the result of insufficient die flow balancing. Most profile dies are balanced simply near the exit. And what we recommend is that we apply a methodology called cross-flow minimization, which is basically to balance the entire die from the entrance to the exit. And our target starts with the final part shape. This is what we want to make. And we analyze the areas of the final part to determine what our target is when we do our flow distribution through the system. So for example, if we want to produce these vertical walls, which represent 1.16% of the total cross-sectional area, we have to deliver 1.16% of the flow to these walls. In other words, the percent area determines the percent mass flow that has to go there. So to explain this a little bit further, if we consider this region near the edge of the die, we have a wall that represents 2.86% 0.86% of the total flow, a vertical channel that represents 1.16% of the total flow, and a horizontal section that represents 2.86% of the total area of that part, which means that the amount of flow we need to deliver there is 6.88%, but not just at the exit. The mass flow in that region must be delivered at every cross-section. So if we do an analysis of a cross-section, here I have the Z direction of 47 millimeters. So let's say in this region, this is what the shape looks like. We need to adjust the geometry, which we can do through the simulation, and analyze the amount of flow in any region. So this region over here that's going to make that wall, and make sure we have 6.88% in that region. Once we do, we export this cross-section, and this is the geometry that the designer will use to ultimately finish those channels. The same thing with this horizontal wall. If we were to analyze the cross-section of this area right here at 172 millimeters, we want to make sure that the flow in this region at the bottom is 34% of the total flow, and this will ensure that we have the right amount of material to make our part. And the same thing with the top wall. At another location, we want to make sure that there's the right amount of material there, 34%, to make the final part. So that once we've balanced all the cross-sections, the polymer doesn't take this snaky pattern through the system, but rather follows a straight-through approach. And this way, we can, by balancing the inlet and outlet of all die plates or cross-sections, we can minimize the cross flows, which improves the stability and maximizes the production rate. And this method can be applied to both multi-lumen medical tubing and to automotive applications or rubber seals and gaskets. And finally, the last topic that I'd like to discuss is coextrusion and coextrusion instabilities. This is an image of a wave pattern in a sheet, and this pattern was observed in a 3-layer sheet which had 2 thick layers and a middle thin layer. And the customer contacted us and asked us to evaluate it. This flat sheet is produced using a feed block. We asked them to send us the design of the feed block, and we analyzed a cross-section using a 2D finite element method. And this is a result showing the velocity in that cross-section. And if we look at the numbers, we see that we have a high peak velocity in here where the lamella were slightly unbalanced, 113 millimeters per second. The middle layer had a maximum velocity of 14.6 millimeters per second. And the maximum velocity just prior to entering the distribution manifold in the flat die was 64.6 millimeters per second. In other words, the middle layer had an acceleration of about 4.4. That is the velocity it had on its own versus the velocity after it merged and just before entering the die. This can be seen a little bit better if we just look at the volume or space that middle layer occupies. You can see that in this area we have a high amount of acceleration or stretching of the material. Now this is fine if the material accepts this stretching, but if we look at the rheology, and in particular here we're showing the elongation or extensional viscosity, the middle polymer was what we call a strain hardening material, which becomes more viscous the faster you pull it. Whereas the other polymers were strain softening, like HDP or LLDP, which the faster you pull them, the easier they are to pull. So think of it as the difference between chewing gum and a rubber and an elastic band. The chewing gum, as you stretch it, it gets easier to stretch. But if you take a rubber band and you stretch it, at some point it locks up, and if you go any further, you can actually tear it. And what was happening in here was that middle layer, right along in here, if we follow this line right here, we show the velocity. So here we see the velocity of that layer dipping down in this point right in here where it opens up a little bit, and then increasing to the 64.5 millimeters per second. And the blue line is the elongation rate. And the elongation or stretching that the material experiences. In fact, we see at this point there's a compression. The material is squeezed where it slows down right in here. And then there's a rapid stretching of the material. And that elongation is 4.5 reciprocal seconds. On its own, this has no meaning, but when you link it to an image of an instability in the product, you say, oh, okay, this elongation is too much for that particular structure, that layer that we're running, and maybe if we reduce this, we can solve that problem. So how do we go about reducing it? Well, if the material wants to go faster when it comes together, we modify the geometries so that the center layer is accelerated, pre-accelerated inside the flow channels of the feed block. So here we've essentially doubled the speed to 26 millimeters per second maximum velocity. The final velocity stays the same because the flow rate and the geometry can't be changed. It all goes into the same die. But by pre-accelerating the material, we've reduced the acceleration to just about in half. And if we look at the space it occupies, that's the same. You can see less acceleration or stretching of the material in this region. And if we look at the velocity along a streamline in there, we see the initial pre-acceleration, and there's a small elongation created when the material is accelerated. But we can control the rate at which it accelerates by controlling the taper angle on the geometry. There's a slight deceleration where the material merges with the other layers, and then there's the acceleration after the channel tapers and the material accelerates to enter into the die. But all in all, the total elongation, maximum elongation the material experiences is about half of what it experienced before. And when they ran the product with this modification, it eliminated the wave instability that they were observing. So that's what I was saying, where you need to correlate an observation to a simulation result. Then you can understand that that deformation is too much. Now we know that whenever we're running those polymers, we can have acceleration over or an elongation over 2.5 reciprocal seconds. Otherwise, we might expect an instability to occur in that system. A similar problem occurs in tubing or cable jacketing, but it's a little bit reversed here. In this case, they had these waves that they were observing in their product, which made it unsellable. And when we analyzed the merge region, we found that instead of having a high elongation rate, they had a very low or negative, very strong negative elongation, which means a compression, a slowing down. So what was happening is that this outer layer of material where they were merging was having a tremendous deceleration at the merge point. And so we suggested that they modify the way the material comes in so that it comes in more of an angle, and that they match the velocity of the material before it comes in to what the velocity of the material wants to be after it merges, and to significantly reduce the amount of deceleration the material experiences in that region. And then they could produce acceptable cable without any instabilities. So for unstable coextrusion process, the solution is to avoid formation of excessive elongation stress or deformation during the merging of the individual layers. In coextrusion flow analysis provides the velocity of each layer in a multi-layer flow field, and we can adjust the pre-merge velocity to more closely match the post-merge velocity and avoid any high acceleration or deceleration. So in conclusion, I hope you see that process simulation provides more information for correlation of material properties, geometry, and process conditions with production problems, and the simulation gives us a better insight into the problems, which can lead to faster and more precise solutions as opposed to traditional trial and error methods. So with that, I'd like to thank you for listening, and I would be pleased to answer any questions.